So first, I wanted to give a little shout out to the funding agencies that have supported us. Our construction of these tools is supported under the Exascale Computing Project, the National Science Foundation, and then some funding from Argonne and Lawrence Livermore. And this is not just my work. I have a team that involves staff, graduate students, and a couple of undergrads. So as computational scientists, you face a number of challenges. The platforms are rapidly evolving as well as your applications. And one of the things that I'm sure you're well aware of is that there's significant architectural diversity. So Cooley is a multi-core system, Theta is a many-core system, Summit has GPU accelerators, and the forthcoming Aurora A21 system also is going to have accelerators. And so what we're seeing is increasing parallelism within the nodes. And then for applications, that means that you're moving to add additional node-level parallelism to your codes beyond MPI. And so you're adding OpenMP or using OpenMP target or CUDA to offload to GPUs. You're probably trying to leverage vector parallelism if you're working on Theta, as well as just adding new capabilities to your applications. And so with all of this going on, the software has to evolve rapidly. And I would argue that it's important for you to use performance tools as your guide to help you adapt to the changes in these emerging architectures, assess the weaknesses in your algorithms and their implementations, and be able to map them well onto these large-scale parallel systems. So for performance analysis, there are a number of challenges. So these complex node architectures are hard to use efficiently because we've got multiple cores, we've got instruction-level parallelism, we've got single instruction, multiple data, vector parallelism, we have accelerators. There's a multi-level memory hierarchy, which means that your CPU is running a lot faster than your memory, and there's multiple levels of cache that are designed to sort of buffer the distance between main memory and the CPU. And if you're not using all these levels of parallelism and not using the memory hierarchy effectively, then there's going to be a big gap between the performance that you achieve and the performance that would be peak on the machine. Don't expect to get peak performance, but you shouldn't settle for less than 5% either. So on our side, from the tools perspective, complex applications have challenges as well. They're hard to measure and analyze. We've encountered some applications that use OpenMP and init constructors for shared libraries. So we've got threads being created before all of the code is even loaded. There are also challenges for understanding the application behaviors and the performance. And the greater the complexity of the application, the harder it is to measure and the harder it is to understand the resulting performance. And these supercomputer platforms just sort of compound the complexity. In the past, we've seen microkernel-based operating systems. Fortunately, that's sort of shifting, and Linux is becoming the standard. But each of these systems has unique hardware. And when you're measuring the performance, you're not just interested in the computation performance, you're also interested in whether your computation is being blocked, waiting for data movement through the memory hierarchy, communication with other processors, or I/O to the file system. So I would argue that what you want are a set of multi-platform programming model independent tools, whether you're using Theta, whether you're using Cooley, whether you're using Summit. It'd be nice if you could use the same tool, just learn one and use it everywhere. And what we want to be able to provide is accurate measurement of complex parallel codes. And the kinds of codes that we've encountered are large, they're often multilingual. People still write some of their kernels in Fortran because it's fast. Often there's C++ frameworks wrapped around it. There's optimized code, which means that the loops get torn apart. There's C++ templates and inlining and all sorts of things going on, in addition to having libraries that are available only in binary form. So sometimes it's platform math libraries, other times it's a vendor's OpenMP runtime system where symbols are stripped out. And then we have complex execution environments. And so on clusters, often you're running dynamic binaries that are loading shared libraries as the application launches. On systems like Theta, on the Cray platforms, often static binaries are used. And so the tools have to be able to cope with both of these circumstances, and then batch jobs as well. So what we're trying to deliver is effective performance analysis that provides some insight into what's going on with your code. And we want to be able to pinpoint problems and say, here it is on such and such line of your code, and also give you some indication of what's going on. And if we don't relate it to your code and we just draw pretty pictures, then there's going to be kind of an air gap between, okay, I can see that something's wrong, I can see that the memory hierarchy is being misused, but if I don't know what loop, what source line, it's sort of hard to take action. So in our own work, we wanted to build something that's intuitive enough for application scientists and engineers to use, and also detailed enough for library developers and tool developers and compiler writers like ourselves. And then the last thing was we wanted to make this scalable to the petascale and beyond. And this is a continual struggle to try and keep up with the scale of these machines, and the exascale systems are going to require a bit of work, I think. So let me give a brief overview of what HPC Toolkit does and how it works, and then show you a couple of things that you can do with HPC Toolkit. And we'll give a few demos of the user interfaces, and then I have some hands-on exercises where you can use the user interfaces on some data that's already collected. And now that I have access to the classroom queue, I'll see if I can tweak the submission scripts for an experiment that you could run and collect your own data later today at some point during one of the hands-on sessions. So let me start with what HPC Toolkit does. It employs binary level measurement and analysis. And so we're working with observing fully optimized dynamically linked binaries, or statically linked as well, supporting multilingual codes with external binary-only libraries. We're using sampling-based measurement principally. If we want to measure things like bytes communicated, well, then we're going to wrap a communication call or an I/O call to see how many bytes have been written. But generally, we're measuring performance by using sampling. And so what this means is that there are these periodic interrupts that are interrupting the program, and we're gathering information about where we are, and we're attributing costs to where we are. The advantage of sampling as opposed to instrumentation is that the overhead is controllable. We have no control over how often you call functions or whether your functions are really tiny. But if we're just saying sampling at 300 times a second, then we know how much overhead we're going to introduce. So when collecting things with sampling as opposed to, say, tracing, we're going to end up collecting a compact representation of the measurement data. If we're tracing every routine that you enter and exit, you can end up with gigabytes of data very quickly. So we end up with compact profiles that facilitate measuring things with large-scale parallelism. And then HPC Toolkit will collect and correlate multiple performance metrics, and you can compute derived metrics by just specifying like little spreadsheet-like equations, and I'll show you how that works. And then we associate these metrics with both static and dynamic context. By dynamic context, what I mean is call chains. So you know that main calls A calls B, and I incurred some cost in B, and I can see how I got there. Now, why is that important? If you have some sort of coupled climate simulation and you find out you're spending time in MPI weight, you need to know, well, is the problem the ocean module, or is the problem the atmosphere module, or something else, right? And if we just know that it's an MPI weight, that's not going to tell us what we need to fix. And so we need this calling context. So we have the dynamic calling context, and then we also associate costs with procedures and lines, which is standard, but we also associate things with loop nests as well, which is not. And to do so, we employ binary analysis of the application. Our tools support top-down performance analysis, so you can identify sort of things of interest, and then you can drill down to their causes by moving up and down call chains or moving back and forth across time. All this will become a little bit clearer once you see a few demos. So let me show you sort of how the tool is organized and how to use it. So you start with your source code, and you compile and link it the way that you normally do. So for dynamically linked executables used typically on Linux clusters, you don't do anything to your make files. For statically linked executable on say, a system like Theta, you might build statically linked executables, or you might build dynamically linked executables. If you build statically linked, then and in the final step, as you're linking your application, you just put our tool in front of it. You say HPC link, and then you give it your compile command and all the rest of it. And then our linker script will inject our instrumentation into your executable so that it's there and can start measuring once the application gets launched. So after we've prepared the program for measurement, then at runtime, we're going to collect these profiles. We're going to collect call path profiles. So we will launch your optimized application binaries. If it's dynamically linked, then you'll just use our tool HPC run to launch it. And so HPC run will then load our measurement library into the address space of the application. If we have a statically linked binary, then at compile time, we've added our instrumentation into the executable, and environment variables are used to control what's going to be monitored. So as the application runs, we're collecting statistical call path profiles of the events of interest. And so the events of interest might be time, or it might be cache misses, or lots of other things, TLB misses. You can measure lots of different things about the interplay between the application and the hardware. So I mentioned that we collect call path profiles. So what does that really mean? What we're trying to do is we're trying to attribute the costs of the execution to the context in which the costs were incurred. So at runtime, we're going to get an asynchronous event trigger is going to fire. And examples of this are a timer where we say 1,000 times a second, interrupt me so I can measure the performance or measure where the application is. Or I might say every million cache misses, interrupt me so I can find out where I'm taking cache misses. And so every one of these interrupts is at a particular place in the code, a particular instruction pointer. And so from where we are, let's say we're in some routine C, then we'll find the return address and say, well, we're called from B, well, who's called from A, who's called from main. So we get a call chain that tells us where the costs were incurred. And then over time, as the application runs, we're going to collect a series of these call chains, and they all get fit together into a tree. And so conceptually, you might think that main is kind of at the top, and then maybe this is an initialization phase and a solve phase and a post-process phase are kind of represented by different subtrees within this calling context tree. And so the beauty of this sampling-based approach is that the overhead of measurement is proportional to the sampling frequency, not the calling frequency in your application. So then, once we've collected this measurement data, we also analyze your binary. We have a tool called HPCstruct, which analyzes your binary. And so what it does is it's analyzing the machine code to identify the control flow and identify the loop nest from the control flow. It's looking at the line map to find out how the machine instructions relate to source lines. It's looking at the information that's recorded by the compiler about function inlining and whatnot. So we're able to extract information about loop nests and identify inline procedures. And then we're able to map all of the machine code back to your source. So when we take measurements at a particular address in your application, we're able to say that machine instruction came from a long chain of inline code. So then we have a third tool that takes the call path profile that we've collected as the program executes, takes this program structure information that we've gleaned from the binary, and it takes those two pieces of information and it knits them together into a comprehensive whole. And it produces what we call a performance database. It's just a directory full of files of various kinds. And when you're using this tool, there's one tool called HPCprof. And so that's something that you might run on a head node on sort of a small number of profiles that we're collecting. So when we measure an application, right now we're collecting a profile for every process, every thread that's in your entire application. And so if you launch something on 512 nodes, then at a minimum, you're going to have one for every MPI rank. And if you're using threads, then you may have many more than that. So what HPCprof is able to do is it's able to take all of these profiles that were collected independently and knit them together. If you're analyzing large-scale data, we have an MPI program to do that. So you launch the MPI program to analyze your performance data. It works essentially the same, except that instead of analyzing it on the head node of your system, it's going to use the back-end compute nodes to do so. So another thing that we can do with HPCprof is we can take data from two separate executions. So you might run it at one scale and then run it at a larger scale, and then you can compare them to look at scalability losses. And then finally, we have some presentation tools. We have one that HPC Viewer that provides a code-centric view. It relates all the application performance back to your source code and to call chains in the source code. And then we have another one called HPC Trace Viewer, which shows you how the execution unfolds over time, and it gives you sort of a time series-like view. And so these tools allow you to explore the performance data from multiple perspectives. You can rank order metrics to decide what's important to you. You can compute derived metrics like scalability losses. And you can graph thread metrics to see if the threads are all working or whether some of them are sitting idle, and look at how things evolve over time. So here's our code-centric interface. It seems rather simple. We've got a source pane. We've got a navigation pane, and what this is showing is a top-down view that has a long, what looks like a call chain, but it's a little bit more than that. And then we have some metrics off to the right in these columns. And so the metrics are whatever you've decided to collect. And so here it was just collecting time, but you can also collect cache misses and things like that. And so the metrics are related to the contexts that are shown over here in the navigation pane. And then there's some view control things, so I can look at a top-down view where I'm looking down call chains, or if I want to find out where some particular matrix multiplication routine was called, where I spent a lot of time in this matrix multiplication routine, and I want to know the myriad places that called it and which one was most costly. So for that, I can use this bottom-up view and say, let's look up the call chains. And so I spent 30% of my time in this routine. Show me where it's called and who's the most costly context. And then there's a flat view that says, well, I don't really care how we got here. Just show me the performance correlated with the loop nests in each of the functions. And then in this navigation pane, we have not just call chains, but on top of that, we've overlaid information like, so this says main, inside main, there's a loop. And then inside the loop, there's a series of inline functions. And we have the source lines where the inline functions are called. And then the inline function calls a real function, which calls a couple more inline functions, which instantiates some C++ templates, which generates an outline procedure for OpenMP. And then there's more inline code inside that. And so these contexts are really rich. And when you're using something like a C++ template framework, you have to track the inlining. Otherwise, we've had calls from folks at Lawrence Livermore National Lab, and they said, so it says that we're spending time in vec.h inside main. And that's not really useful. What you need to know is whose vectors and how do they get there, and that we have like 3 levels of inlining that brought all of this stuff into main. So tracking all of this is a big thing that we've done in our binary analyzer, and that's the reason for it. So when you're using these large-scale systems, it's often difficult to get the scaling behavior you want. And so as you increase the number of processors, what you'll often find is that instead of scaling at a parallel efficiency of 1, that it starts to tail off. And so the question for you as an application developer is, why is it tailing off? What's causing it to tail off? Is it the way that I'm doing I/O? Am I partially replicating computation? Is there too much data movement in the memory hierarchy? What's going on? So answering that question is the thing that you really want. So we have a strategy for doing this largely automatically. So we want to be able to pinpoint scalability bottlenecks, guide you to the problems, quantify the magnitude of each problem, and then ideally we'd like to diagnose the nature of the problem. Well, it turns out that the last thing, diagnosing the nature of the problem, is often more art than anything else. And so what we can do is we can identify the scalability bottlenecks, quantify them, and pinpoint them in your code, and then you're left to stare at the code and say, why is this not scaling? Okay? But often, the indications that we can give you and putting you exactly where the problem occurs, you can look at what's going on around there and figure out both what's wrong and how to respond to it. So let's consider an example here. So let's say we have couple of climate application. And so modern applications use lots of layers of libraries. So there's solver libraries that are using core math libraries, and there's MPI and whatnot. And so we have our climate application that's doing land and sea ice and ocean and atmosphere simulations, and at the bottom, MPI weight inside each of them. And what we want to be able to do is find out if we're spending time in MPI weight, we want to know which of these phases is the problem. So when we're monitoring, we don't know whether the bottleneck is communication, computation, or synchronization. And the pragmatic constraints are that we can't collect too much data, and we don't want to disturb your application's run so badly that you can't afford to run it. So if we dilate the cost by a factor of 10, that's not so good. We'd like it to just be a few percent. So our methodology for performance analysis for tracking down these kinds of scalability bottlenecks is we rely on you. Okay? You have some expectations for your code. So if you are taking your code and you're taking the same size problem and you're running it on twice as many processors, typically you want it to be twice as fast. Or if you run it on twice as many processors but you double the problem size, then you would typically expect it to have the same amount of work per processor, and it should take about the same time. So either you're strong scaling, where you're just increasing the number of processors and we expect the time to decrease proportionally, or you're weak scaling, where you're doubling the number of processors and doubling the size of the problem, in which case, when we're running on the larger number of processors with the larger problem size, we expect the time to be roughly the same. So from that simple idea, we can put your expectations to work. So what we do is we measure performance under different conditions. You run it at one scale, and then you run it at another. Then you express your expectations as an equation, and I'll show you what I mean by that. And then you compute the deviation from the expectations for every calling context in your program, and correlate this with the source code, and then explore the result. So conceptually, how does this work? So let's say that I run something on 256 cores. And I've got my calling context tree, and the intensity of the colors here indicates how much cost I've incurred in each one of these contexts. And then I run it on a larger number of cores. And so I have a different distribution of costs on this larger number of cores, because maybe I'm spending more time communicating or something like that. So let's say we spent 400K units of time in part of the calling context tree that represents the solver. And then when we ran it on a larger ensemble, then we spent 600K units of time. So if we're if we're strong scaling, then we expect these times to be exactly the same. That's our hope. But as you add more cores, they're dividing up the work more finely, there's more overhead and whatnot. So we take the difference between this overhead, and this is wasted effort. So we can divide the wasted effort here by the total amount of effort that we put in. That gives us our fraction of wasted effort. Multiply by 100, that's our percent wasted effort. And this percent wasted effort is actually the same thing as percent scalability loss. And so with just a little bit of math, we can calculate these scalability losses, and then the tool can show us everywhere where they exist and quantify them and allow us to find them very readily. So let's look at an example. So here's a code that was developed at the University of Chicago for simulating astrophysical events. So helium burning on neutron stars, also things like nova outbursts on white dwarfs. So we ran a simulation of a white dwarf detonation, and this is a canned data from a while back on a Blue Gene P, and we're comparing simulations on 256 cores versus 8K cores. And this is weak scaling. So let me show you the user interface. So I think with the high resolution here that the text is so small that you can't see it, so I'm just going to zoom out a little bit. Okay, so what this says is we're spending our time in program Flash, and then if I just click this flame button, then it opens up and says, well, there's a call to driver evolve Flash, and inside that there's a loop. Now it doesn't point at a loop. In fact, the loop is a few lines above. And the reason why it doesn't point exactly at the loop is we're gleaning the source mappings from the machine instructions. And so we see that there's a loop there, and what we found was the first source line that was inside the loop, and that's where the machine instruction came from. So, so we can look at this for the performance for 256 cores or some other columns here for 8K cores. But let's just focus on this idea of the scalability losses. So what I can do is I can take my time on 8K cores, and then I will subtract the time on 256 cores. So this is weak scaling, so I expect these to be the same. So any difference comes out is wasted effort. And then I'm going to divide that by the total amount of time on 8K cores, and I'm going to multiply it by 100 to get my, instead of a fraction of wasted effort, that's my percent wasted effort, which is the same as percent scalability loss. And I'll display that as a percent. And now I've got another column over here. And it says that I've got a 24% scaling loss. And then I can go and say, well, let's look. So here we have, of the 24%, 14% of it is in driver evolve Flash, 10% of it is in driver init Flash. So let's look at the initialization first and say, show me the scaling loss. And it dives down into the application, and it shows me that the losses are occurred at this loop nest here. And what I can see right above me, it says loop through all processors. Okay, so now if I increase the number of processors from 256 to 8K, then I'm going more iterations around the loop. I'm doing more work. So I didn't know that. I mean, this isn't my code, right? But the point here is that we're able to just zero in on this, and it tells us, well, here's a problem. And then we look at it and we say, well, of course, the loop is getting larger as we use more cores. So what's going on? Well, then this is where the diagnosis comes in, and this is what, what's up to you. So it turns out that what it's doing is it's circulating messages around a ring. And so they're after the adaptive mesh refinement, everybody's got a piece of the domain. You need to know who's your neighbors. So you say, this is what I've got, and then you circulate it around the ring, and then you watch the stuff that comes around and say, oh, I need to talk to this processor because he's got my left face. Okay. So I could show you other examples in here that point to barriers, that point to serialized I/O, but this is the basic idea. I'm sort of running out of time, so I want to show you a couple of other things. So this is our code-centric interface, and with a little spreadsheet-like equation, I can just zero in on this scalability loss, and I can also look at other losses by just pointing at different places in the program and say, underneath the evolve phase, show me the losses in the evolve phase. Okay, so in this profile view, we've collapsed out the time dimension. So Another thing that we can do is with our sampling-based performance measurement, we can retain a series of samples over time. And so as a thread executes, we can collect a series of call stacks for that thread and do this for every thread in the program. And then the idea is that we can visualize the performance by moving this visibility plane up and down. So we move the visibility plane all the way up to the top and see what's everybody doing at the top layer. Oh, everybody's in main. And then if we push it down one layer, then we might find that, well, early in the program, they're in the initialization phase. Later, they're in the solve phase. Later, in the post-processing phase. And you push it down a little further, then you see, well, within the solve phase, there's a series of iterations and a bunch of other procedure calls. And so this is going to give us a high-level view of what's going on in the application. So we're n times a second. We're going to take a call path sample of every thread. And then we're going to visualize how the execution evolves. So let me show you what this time-centric interface looks like. So this is the same code, the Flash code. And so we're up at the top of the call chain, and it says that everybody is in Flash. And if I move down one layer, then we see two different colors. This is the initialization phase. This is the solve phase. We move down another layer. Now we can see, okay, so now the iterative behavior starts to appear during the solve phase, and we can see every few iterations there's something different that happens. If I want to know what happens, I can just point at a color and say, whoops. If I want to know what happens, I can point at a color and say, what is this? And it gives me a complete call stack of what happened on that processor at that point in time. So it might look like this is like we're collecting an enormous amount of data, but in fact we're only collecting 12 bytes for every sample. Because essentially we have this calling context tree that says here's all the context in the application, and then as we're collecting these measurements, we just say, okay, so again I was at node 17 in the tree, which implies an entire call path up to the root. So you can look at your application at multiple levels of detail and identify program features, and there are things like synchronization and whatnot that become readily apparent, where there's some sort of load imbalance, and then everybody is here waiting in an all reduce, waiting for everybody else to catch up. And this stuff is sort of really easy to spot with this kind of interface. All right. My time is slipping away. All right, so another thing that we have is some support for OpenMP. So there's a large gap between threaded programming models and their implementations. And so I worked on the OpenMP Standards Committee for a while, and we defined a tooling interface for having the runtime system give us some information that allows us to relate the implementation level view that runs on the machine back to the source level view. So the design objectives for this interface were both to provide some assistance for tools and give us some information that we couldn't get otherwise, but also if the vendors were actually going to accept it, then it had to have essentially zero overhead if it was turned off. And so we worked pretty hard on defining this interface, and it was, for OpenMP 5, the interface was announced in November. And so we're in this mode where everybody's trying to sort of finalize things. I think the Tau group is all set with their use of the OMPT interface. And we're still refining a few things because we're also working on Intel's open source runtime, that we use a different feature set than they're using. And so there's some issues that still need to be fine-tuned. So what this gives you is, instead of having a master worker kind of view, it allows you to take all the worker views and take these computations that were outlined by the compiler, instead of having a worker thread pick up some piece of work that came from who knows where. Now we can see the cost of that work attributed to the calling context where you wrote it in your program. So not only can we see these sort of full calling context-like views for OpenMP programs where everything is unified together, but we can also have this thread level view where we can see how the load balances over threads. So we're able to, using this OMPT interface, it unifies the views across the threads and the main processes. And so it's helpful for doing things like the scalability analysis as well, to not have these two disparate classes of threads. I mentioned the status. There's still a little bit of ongoing work, but it's all starting to gel, and I expect within the next few months that most everybody is going to have this under control. So the last thing I wanted to mention briefly is that we've been building some support for measurement on NVIDIA GPUs. And so what we're measuring are kernel invocations and data copies, and a unique thing that we're measuring is PC samples. So these are program counter samples on the GPU. Now, actually, NVIDIA's library, their performance monitoring library, is measuring this. What's unique about our tool is the way that we're interpreting this. So we are using the OMPT interface to understand when a device is initialized and code is loaded or unloaded. And then we get a bunch of information that streams back from the GPU where it's telling us, here's these measurements that I took, and then it's up to us to ingest them. And I don't have time to go through this in detail, but let me just show you. So here's a little snippet of a vector add, which calls some helper function. And so by the time this vector add and the helper function are compiled, these two calls, in fact, become 6 calls each, sort of strewn around the control flow. Well, what we're able to do is to get a call path profile for the code that includes the cost on the GPU. And so what we can see is, here's the calling context tree for vector add, and then inside that is one loop, and then there's a set of calls inside that, and then there's the other loop, and then there's a set of calls here. Why do we have 4 calls? Well, we've made the decision that we don't collapse call sites together. So in fact, it's showing us that there are 4 different calls associated with the same line. And what I showed you is actually, after the compiler optimization, it's generating 6 calls, of which 4 we measured were actually used. So we're able to show these calling context trees with costs all the way back into the GPU, and then show metrics like instruction samples and stalls to pinpoint bottlenecks inside the GPU performance. So this has been emerging over the last 2 years, and it's really sort of started to gel over just the last few months. We've been able to use it for measuring the same application that I showed earlier on the CPU side. We're measuring it offloading code onto the GPU, and we can associate costs with individual loop nests in the GPU kernels. So a couple of final notes about other things that we can do. We can measure hardware counters. We're using the Linux facility for doing that, called perf events. And so we can do things like frequency-based sampling to say, I want to sample 300 times a second, and then the machine will, the subsystem in the kernel will figure out exactly how often to monitor this in order to deliver samples at the desired rate. It can multiplex different events, and so typically these systems have only a few hardware performance counters, and if you want to measure a large number of events, then the perf event system will multiplex that. So not only do we measure cost in the application, we can also measure costs of time that your application spends in the kernel as well. And so some of the things like allocating and clearing memory pages. So memory allocation is something that it's easy to get wrong, and if you don't do it right, you can end up spending a lot of cost surrendering pages back to the kernel, and then when you allocate, you're acquiring pages from the kernel and then zero filling them to make sure that no data is leaking from process to process. Some things that are ongoing are we're working on making things comply with the OpenMP standard. We're improving our support for measuring these GPU accelerated nodes, planning ahead for the forthcoming Aurora A21 and Orinel's Frontier system. We're working on attributing costs not just to code, but also to data, so you can find out which are the costly variables in your application. And our planned work for the future is to scale this whole thing out to exascale and to support top-down analysis methods using hardware counters. And so in this context, top-down is going to be looking at time spent in communication, in computation, in the GPU, in the CPU, and then also some resource-centric performance analysis within and across nodes to know, have I consumed all of my bandwidth? And these are important things you need to know for your application. So I'd be happy to take a few questions. Otherwise, we'll have some time to work on some hands-on exercises, and I can answer more questions later. So, any questions now? Yes?
What about other threading approaches than OpenMP, like POSIX threads or TBB? Just that they don't show up nicely, or?
That's it. It's just that they don't show up nicely. So what you get to see is effectively the implementation level view. So the difference is that OpenMP, you have this high level view where the compiler derives the implementation view. If you're programming with pthreads, you're writing the implementation view. So we just show you the implementation view is the source view. Okay. Other questions? Yes?
When you're doing the comparative analysis with the flash code, comparing 256 to 8192, could some of those insights have been revealed at lower core scaling, like with 12 and 256, or that's only possible with that many cores?
So sometimes you can see these things at smaller scales. But other times, the scaling bottlenecks only happen when you start overwhelming I/O nodes or things like that. So what I would say is you start with the smallest scale where you find that you're getting insight into your code, and you analyze it at a small scale, and you don't burn too much of your allocation. And then once you're happy with that, then you double, right? And then you double again. Okay. Other questions? Okay.
I have one question. So you talk about you plan to support coming exascale system, Aurora and Frontier, for OpenMP. So do you also plan to support some vendor-specific programming language, HIP or SQL?
Right. So this is the challenge is that we have both this high-level OpenMP programming model, and then we have a low-level vendor-specific programming model like CUDA or AMD's HIP or SQL if that's Intel's planned low-level model. So right now, we just introduced we're proposing some changes to the OMPT interface that will make it easier to coordinate measurement both through the OpenMP interface and of these external programming models. So right now, we support measurement of CUDA and we support measurement of OpenMP, and we plan to generalize that to whatever the high-level, low-level model is on these forthcoming systems.
Okay, cool. Okay. So any other question? Okay, otherwise, please thank John.